Drones to drills is a new exploration technique that Ground Truth and I, Sean Ryan, have been working on for the last 4 years in developing in the Klondike district out of Dawson City. The idea was that, through the big 2010, 11, basically up to 2012 rush, we conducted very large soil sampling programs, which led to discoveries such as the white golden saddle, which is 1.5 million ounces. Then we found the coffee deposit system, and that was about 5 million ounces outlined so far. But as everything started to slow down by 2012, we decided to take a break, like this prospector. And we were sitting there, in the bush, scratching our head. The old system worked, but can we come up with a cost-effective, environmentally friendly way to gather high-quality data in the Klondike so that we could extend our budgets for working? So the idea is that we came up with the drones to drill kind of technique, and it was answering one question at a time. So the first one was, can we gather high-quality data, such as drone imagery? So that was the 3D blueprint of the work site. Then the next question was, under these soil anomalies, can we actually map out the structures? So we ended up moving into DC resistivity, and it was at 5-meter electrode spacing, so it was very high res IP, and that actually helped us outline the structures. Then the next question everybody had is, which structure is anomalous? So then we, instead of using these little mini excavators that we used to use, we designed this GT probe, which is a hammer drill on these special rubber tracks that basically could sample with no environmental liability. And everybody's next question is, how deep does the mineralized system go? So we actually put a rotary air blast drill on the same rubber tracks and kind of modified it and came up with a GT wrap. The next thing is we tie everything together as in a video package so that we can make the presentation to the client. So it's a step-by-step approach, and it's a process that allows us to actually gather data and think about it as it comes through the system. So here is air photos the drone way now, and these are these little EBs that we gather the data in. So the EB weighs under 1 kilogram, and you can hand launch it from a helicopter pad. It's autonomous, it flies on its own once you set up the job. And it roughly has about 35 minutes to 40 minutes. And here, once you launch it and it takes off, here's the program that comes with the package. And then we just lay it out, how it's going to land, the size of the grid that we want to cover. Then we actually put in the resolution that we want to pick up. And it actually figures out on its own, like it lays it all out, and then it takes off. And then after about 35 to 40 minutes, it comes back, and here's the target we're trying to hit. Look at how close she comes. Ooh, we almost hit her. So that's the whole point with this thing. You launch them from almost anywhere, and basically they do their magic and come back, and then we start playing with the process data. So then we create these 3D models, and that's the whole point now. This is one of our 3D models after post-processing. Now, if I want to go to where this star is, just like Star Trek, beam me down, Scotty, and look in this general direction at that ridgetop, this is what it's going to look like in the model. This is like looking out of a helicopter right now. So it's that crisp and clear. Now, if I want to actually add geology, geophysics, the soil geochemistry data to this, now we could actually add those layers on top of this. So this is where we brought it to. What's real, what's not. This is a shot of the tombstone, one's a picture, and one's a 3D model. So it's quite life looking, real life looking, so that's what the whole point about this is. Then we create these nice cool videos that you could fly around. And like, this is Map Info 3D. So once you put the data in there, the 3D model, now you could fly around in the model and look at various aspects of the, here we're going to fly over the Tombstone Mountains, those high peaks. Those are 7,200 feet, and that's what it looks like looking down. These are 2,000-foot verticals that we're looking at. So the idea is that you could fly around and look around the valley. Depending on the resolution, you can see how crisp and clear it really is. So the next part of the project was, what we're trying to do is map out these big soil anomalies. And what happens is that these big soil anomalies are like lots of smoke. Where's the fire in there? So we looked at various techniques, and we settled in on a system called DC resistivity, which is high resolution IP surveys, but it's on 5-meter electrode spacings. This is the latte right in here, and look at how well that picked up the target. This is like a half a day's work, and that's what it looks like over here. So once we did this first case study, we knew we had an interesting product. This is what the idea of it is. It's just like a receiver, and there's a Honda generator that works with it. And here they're watching the data as it's gathering and plotting it out. But the real cool part about this is you're actually not carrying cables. Or pulling cables to the bush. You're actually carrying them and laying them out, reading, and then picking them up. So the idea is we don't actually have to cut lines. This is what it looks like. These are 3-meter electrode spacings. Now this is for the highway work, but that's kind of the configuration you're looking at. Now again, this was the interesting part about this. This is what our lines look like. You don't really see lines. They're going through the bush, but we can wiggle our way through the bush because we're not dragging cables like traditional IP. We're actually laying the cables out, and once we're done, we pick them up and then we move them. So, and then what we do is we use a differential GPS to actually run down the line. So now we get exactly where the line's located, and we get terrain corrections. So now back to the test. Can we find the ultimate test, the T3, T4, T5, multiple structures being caused by one big smoky soil anomaly? This was our first test. This was the results. Here's T3 showing up as a resistivity low, T4 showing up as a resistivity low, and T5. And that's what this kind of survey ends up showing us. And here, because we had sulfides with it, we could see that the T3, T4, T5 actually has a chargeability anomaly also with it. But the bulk of our case studies show mostly resistivity lows. And here we have the QV, where we tried another project, about 300,000 ounces, and you can see this nice thrust fault showing up as a resistivity low. Brought it to another case study. This was the Claza project, and here you can see this is a granite, basically. But again, you can see the resistivity low, which is a structural break coming up through it, and she's lighting up. And again, because it has sulfides, the idea is that it showed up with the chargeability. And here you got the diagram of their dikes swarm coming up with the mineralized zone. So the real trick, what we're trying to do is, if this is a soil anomaly, I'm looking for these resistivity low, basically cracks. And the idea is, this is where we would send in our next tool to actually work this area right here. So we're using the DC resistivity as a filtering tool for the GT probe. The GT probe was designed on these special rubber tracks that we brought in, and we put a hammer drill on it. And the idea was, instead of trenching, we could actually hammer drill our way down on 5 meters. And the idea was, this is what our GT probe survey area looks like. It's what you don't see. You don't see any big trenches or nothing like that. And this is versus the traditional way, which was a 220 hole, digging deep trenches, causing environmental problems and getting a few people upset, And this was even better than our little mini excavators that we actually thought were better than the 220 hose, but they still left some nice sized trenches in it, and you still had to eventually go backfilling. So the idea is that, at 1.2 pounds per square inch, the GT probe, left minimal surface disturbance. Again, you could work in rough terrain. You could fly it around in 2 loads with a helicopter. It was agile. It was, remote control. The guy could walk behind it. And it was 2 sling loads out of the bush. So the idea, here's another little video again. And the idea is that you can see how it sits in a bush. It's not like nice and small. And the guy, it's robotic control, wanders his way through. You can see all the vegetation flipping up behind, even through a little bit thicker bush. So again, it's low impact, not really disturbing the moss. Look at how it even climbs some nice steep hills. Again, no tracks, and that's what the whole point about this is, minimal impact as it's starting to work. So here's a shot from the air, and it's what you don't see. You don't see any big trenches, and all you see is trees moving as it waddles its way through. And that's the idea that, again, we're not leaving big, basically linear lines in the bush. So again, the environmentalists, First Nations, and the Yukon are happy about that kind of solution. Here you can see it's an open face bit, and we're pounding our way down, and that's the idea that we're trying to get a representative sample from either 4.5 to 6 feet down. So then the technician pulls the sample. Sometimes we have a geologist working on site, and the idea is that they get to look at the chips. Then we've tried this system in the wintertime because you can never get a sample in the wintertime, and sure enough, this thing's floating on the snow. Tried it at 35 below, which we could never get a sample, and sure enough, this thing can pound a hole down 4 feet in about 45 seconds. So this added a whole new component. Instead of trenching with a hole, it was the GT probe. Here's a strip log of the GT probe of one line, and the idea is that what you could see is, here you could see the gold that lit up with the XRF, arsenic, antimony, moly, and that was a signature with iron for that deposit. But here you can see another zone right here, and this is where we're getting live feed. So the idea is this is where this line was, but now we could actually make a decision and do another short detailed line for the next day. Here's another example where we ran a line, and this is the gold, and you can see how it's lighting up here. But here's a unique thing. Here's gold, ICP-MS, and here's gold with the XRF, and you can see it lighting up. And again, the arsenic is correlating with it, and lead and zinc. So you can see how the XRF and the ICP are actually working quite hand in hand. So this truly gives us a way to hunt with it, and then the guys can get real-time feed. So if we're hitting anomalous, we're on 5-meter spacings through it, and then as soon as we hit a dead zone, we could actually jump 10 meters and then go back into 5 meters when we know we're into the zone. The next question that came in after this one was, can you guys now drill the target? So instead of bringing diamond drills, we came up with this GT RAV. It works on the same track platform as a GT probe, the same size, same width, so we could actually come down the same lines if we had to. Here you can see again, very, very minimal impact. It's just on rubber tracks. We don't need a pad, so there's no pad building. Again, she kind of hides in the bush. The other interesting part that we've done with this is we put the compressor in one location and we load it up with fuel. Sometimes we actually put a week's supply of fuel in, and we can run up to 500 meters away up to the drill with just lay flat hose. So that gives us, so now we don't need the helicopter to work with. Once we're in sight, we could camp there for a week. So the GT RAB was designed by Ground Truth. And again, here you can see it's robotic remote control, so the operator could walk behind it. You could actually even see how this little flower here, and very minimal disturbance. You can hardly see anything there. So then this thing is going to walk in, and where the picket is right here is where the drill hole spot they want drilled. This thing backs up. You don't see any helicopter support here. Now she's ready. We tried it at 35 below, and she'll drill in the wintertime. The guys don't like to drill that cold sometimes, but if we have to get the job, we can actually get the job done. Then we tried various angles and pushed the outer limits, so the max will probably drill with an open hole is around 50-degree angle, but we can do it, and that's pretty well cut our drilling cost to about 25 cents and $1 compared to diamond drilling. Now the interesting part about RAB drilling that had kind of a bad rap a little bit was the cross-contamination because it's an open hole. So what we did is we did some case study, and here's one where a high-grade section, we had 20 grams over 1.5 meters. If there was absolutely nothing in the next 5-foot section, it was a half a gram, and the next 5-foot section was 0.3 grams, and then nothing. So that was a 10-foot tail. And then when we go through 2-gram intersections, usually the next 5 feet, if there's absolutely nothing, it was 0.3 grams and then nothing. So that was a 5-foot tail. So we could see the little tails and we could live with that because of the cost savings. Once we had that done, the next one that everybody was quizzing me on is, well, you could RAB drill for very cheap, but you can't get the structure. So what we just did is we implemented this we brought in this new televiewer, a downhole survey tool that allowed us to actually go down and measure or map out basically the structure. And the idea is that this survey tool goes down and gives us a representative, an oriented picture of the inside of the RAB hole. And then from here, the guys could pick their different various structures, plots it out in the stereo net. And the idea is that here you can see it right on survey site. But the geologist could actually look at it as it's going down and actually start making interpretations right away. And so this is like live in the field. And here's an example of the televiewer data right here with the XRF data plotted right up next to it. So the idea is that now the geologist can see exactly where the mineralized zone is and then actually blow up the televiewer data and actually see it exactly what's causing the anomaly in that area. So we're doing this by roughly, the RAB hole takes about 12 hours to drill for 100 meters. So they're done by 7, 8 o'clock. The televiewer guy comes right in right behind him. Takes about an hour and a half to produce it. So we could do the structural interpretation usually within a half hour to 40 minutes. So by 11 o'clock midnight, we could actually have this kind of figures going out through the satellite link up to all the geologists that are involved in the project so they can make a decision. So in the back end, like I said, is what we try to do is we actually try to tie all the data together. So here's some of our drone imagery with our soil samples plotted on. And the idea is that we could actually create this nice little video presentation for the company so that they could bring this to the market so we could raise more money. So here's the soil contour lines. The drill holes just got plotted on there. The blue lines are where we ran some IP. So now we're going to go compare the drilling to the IP lines. So here's the drilling. We're going to plot the IP. Now the resistivity low is the blue, so we're going to just cut out the resistivity high. And the blue is the structure. It's where the mineralization, the fluids, because they've been showing up as resistivity lows. But you see the correlation quite nicely with the drilling and the blue zone. So this is basically the package that you present at the back end. So the idea is that once you present all this package, like exploration is like a painting. With every layer, the picture becomes clearer. And so that was the drones to drill package. Cheers. Thank you.